Hi, yeah. So I'm here to talk about quantum statistics in Bohmian Trajectory Gravity. I'm going to talk about the BMV experiment, which is an experimental proposal to look for the quantum nature of gravity, and it should be realizable maybe in a decade or less. So the sort of easier title of the talk is how to get quantum entanglement with classical general relativity in the BMV experiment, and that's the what I'm going to be talking about. And I have an asterisk on classical because it's almost classical, or maybe it's fully classical, depending on how you look at it. So the BMV experiment was proposed in 2017 to demonstrate that gravity is quantum. And the consensus in the papers is entanglement in the BMV experiment shows that gravity is quantum, or at least non-classical. And a great paper to start on this perhaps is the Rovelli-Christodoulou paper, where they say that they strongly hope that the BMV experiment is realized soon, not only to provide a good argument against the persistent and, in their opinion, misleading idea of a necessarily classical space-time, but more excitingly, to give us a first genuine quantum gravity experiment. And it is exciting. So, and there's lots of papers around about it. So here we go. This is how you do the BMV experiment. You take two particles that are quantumly heavy, around 10 to the minus 14 kilograms, and you let them drop side by side, and they have an embedded spin in them, so you can separate them into a left-right state with a Stern-Gerlach mechanism. So they start in the spin up state, and which is plus Z, say, and then they're spatially split into L and R states, and the particles drop through the experiment at the same time, and then through a second Stern-Gerlach where they're brought back into the up-down state. So the initial state at the top is up for one and up for two, and it's just very simple left and right. It's just straight up quantum mechanics. And when we combine those states with a product state to get the initial state of the whole thing, we see at the bottom of the slide there, the initial state is just as simple as it is there. So in quantum gravity, in other words, the consensus viewpoint about how gravity is supposed to work on a quantum scale, you take the initial state to be the same at the top, and it's just the sum of those. It's the product state there, and then as it drops, you can see that when the particles are close together in that branch of the state, the gravity can interact with each of the two particles, and it's actually gravitational time dilation that is responsible for a quantum phase change. And you're looking for a phase change of pi to make the experiment as large of a signal as possible, and to do that you drop these particles for about 2 seconds or so, and maybe a few hundred microns apart. And what happens is, because they're so heavy, the quantum Compton frequency is so high that to get a pi phase shift, just that small time dilation will give you that. And when you if you run the experiment in the future and someone does it and there's quantum gravity, they will get that quantum gravity state, which is down near the bottom there. And it's, as you can see, it's entangled because of the minus sign, which is from the pi phase change. And you can't separate that state back into the two states. So that's the quantum gravity thing. There's entanglement. So in what everyone in the literature talks about is mostly the semi-classical gravity comparison to that, which is that there's no entanglement. And we can see that because we start off with the same state, and then each of the particles gets separated into a right and a left for their in the branches, but the gravitational field is bound to the expectation value of particle 1 or particle 2, which runs down the middle of the experiment, and therefore particle 1 and particle 2 are too far apart to have any gravitational interaction. So you end up with the same state as you started with. There's no entanglement. So now we look at the same experiment again, only with Bohmian trajectory gravity. And of course, the initial state is the same again. And then we look at this in what I call a Bohmian style. It's not 100% true Bohmian mechanics, because Bohmian mechanics recreates quantum mechanics perfectly. But in this case, we've just said, okay, ignore everything else, but let's put the mass of the particle with the particle position, in Bohmian mechanics. So the mass of the particle travels with the Bohmian location of the particle, and you have the 4 possible runs of the experiment as you run it. You have no idea which one, of course, runs as you do it. Well, we'll see about that. But in the first case, the particles go down the left and right opposite. There's no interaction. In the second case, you can see the particles get close to each other. So there's some gravitational interaction. And in the other 2 cases, they're also far enough apart that there's no interaction. So we have a mixture of quantum gravity and a classical result. And so 3/4 of the time, there's no gravitational interaction, and the final state is the same as the starting state. Well, 1/4 of the time, there is gravitational time dilation, and the final state will be the same as that for quantized gravity. So you end up getting a mixed state from a pure state after many runs. And here I just show it as 75% in the no entanglement state, and 25% of the time you get an entangled state. Now in the paper, we do it all with density matrices and everything, but here it's very simple to see anyway. The 25% of the time you're going to get an entangled state. So when you run a witness operator on the full mixed state, you still get entanglement. And that's the crux of the work, is we can demonstrate that you can use classical gravity to create entanglement in the BMV experiment. And how does this work, considering that most of the literature basically says the opposite, that if you see entanglement, you're proving that gravity is quantized. But here, what we're seeing is that in this model, gravity reaches into the hidden variable location in each quantum state and is able to connect that way and then produce some entanglement in the final state. And if this seems strange, I don't know what to say, but I think that the Rosenfeld semi-classical gravity model, which everyone is used to, where gravity is connected to quantum mechanics via the expectation value, is in many ways far stranger than the Bohmian model, because the Rosenfeld semi-classical gravity is an expectation value, and gravity is therefore running, essentially having to compute.
Thomas, 2 minutes.
Yes, no problem. Yeah. So the Bohmian, the Rosenfeld system has to somehow in real time integrate over everywhere to get the expectation value of the quantum state as it evolves, which seems like, to me anyway, a much bigger job than simply looking at where one of these hidden variables is in the Bohmian theory. So my summary is that whether or not you like Bohmian quantum mechanics or not, this is an example of a classical single valued non-superposed gravitational field that can cause entanglement in a quantum experiment. And yet you could argue that it's non-classical because it can see into the hidden variables of quantum states, but you need some kind of channel for gravity to see into a quantum state, because otherwise there'd be no connection at all. And the other thing is an experimental prediction. If this experiment is performed and it provides a lower amount than the full 100% of the full quantum entanglement that is predicted by quantum gravity, then that leads to some sort of experimental value in this Bohmian system. And thanks for your time.
Thanks, Thomas, for the nice talk. Thanks. So let's wait questions from the audience. Sorry, can you comment about what is this witness operator of entanglement? Is the usual purity of the marginal state or what it is?
It's basically just a way to, because you're in an actual experiment, you can't see the state. So what you see is expectation values of running different of different measurements, and then you subtract. I wish I had another slide, but you can make up these witness operators that you do a measurement on X and Y, and then you minus the result of doing Y on both of them, and then if they're entangled, you'll get a positive result. I don't have the details exactly right in my head right now, but the idea is that witness operator gives you a number that shows that your state is entangled, and you can think of better or poorer witness operators as you go on, and there are better measures than witness operators to do this, but that the literature is mostly using witness operators.
Okay, thanks for the answer.